Hello, it's Andy here, and welcome to episode 10 of my SANS 2018 Holiday Hack walkthrough. Our main objective this time is to help Alabaster Snowball deal with a malware infection on Santa's server. Before that, we'll pay a quick visit to Shinny Uppertree to help him with the final Cranberry Pie Terminal challenge. Shinny's terminal is running a lottery program, and he wants to win the lottery. We'll start off by running the program a couple of times to see how it's working. Each time it produces a different random number. There's probably some simple decision logic to test whether the random number matches the predefined winning number and to produce a different output depending on the result of this test. We can use the strings command to extract all of the text strings from the binary. We see the win and lose messages, and also that the winning ticket number is 1225. We also have a big block of base 64 encoded data, which, given previous terminal challenges, is probably some beautiful ASCII art which gets shown upon successfully completing the challenge. We can use the object dump command with the -x argument to list all of the sections of this binary application. We see main, which is the starting point for all executables, calls to several glibc functions including the random number generator, and functions called sorry and winner winner. We can make an educated guess that these are probably the code sections which are run if our ticket loses or wins respectively. We can run our app with the GDB debugger to examine and fiddle with its operation. If we use the run command, the code will run normally unless we interrupt it or it encounters a runtime error. Let's see if we can force the winner winner function to be executed. We'll restart execution of the code again, but this time we'll use the start command. This interrupts the program's execution right at the beginning, letting us inspect or change values in memory. The J command for jump lets us jump to another function. Pressing tab lists all the functions, and here we see winner winner again, so let's just try resuming code execution from that point. And success! We've won Shinny the lottery. We'll leave him to decide what he does with the winnings as we head over to see Alabaster Snowball for the main objective. We join Alabaster as he's battling a ransomware infection on Santa's servers. In the first instance, he needs us to develop a Snort rule to identify any machines which have been infected by the malware. The extra info file tells us that we have access to a packet capture of the last 30 seconds traffic from this terminal, and that the last 5 minutes of packet captures are available on a portal. It's good they're available from a separate portal, because that means we can at least download them and use Wireshark for analysis. We're also given a handy reminder about how we can test our rules before putting them live. Let's start by taking a look at some of the last 5 minutes of packet captures. It's all DNS traffic, and all TXT DNS requests at that. But there seems to be two types of request, some to seemingly random string subdomains of a couple random domains, whilst others are some random word subdomains of genuine looking domains. The former is definitely more suspicious looking, so we'll focus our attention there to start with. The response to an initial query is just 64, followed by subsequent requests 0, 1, 2, all the way up to 63. These 64 subsequent subdomain requests have longer responses. This could quite likely be an encrypted or encoded payload being transferred. Maybe the malware infection starts as a dropper and then retrieves the main payload over DNS TXT requests in an attempt to evade network-level antivirus filters. It's a similar story in other PCAPs, just with variations on the domain names. A long random string is not common in valid URLs, so let's try using that as the basis for our Snort rule. We'll build it up piece by piece. First off, we'll write something which will identify DNS packets. Here, any UDP packet where the destination port is 53. We're helpfully given a message by the terminal that we're not alerting on all ransomware. No issue, we're just getting started. If we run the test command, we're given an error about an ID number being required, so we can go back and add that in and rerun. Then, reviewing the alerts file, we see our rule is being triggered on any DNS packet. Let's tighten it down a bit. We're looking for a string of 38 hexadecimal characters, so we can use the PCRE rule option to specify a regular expression to match against. It looks like we still don't quite have it. Our rule is alerting on any outgoing packets based on a destination port of 53, but maybe we should also alert on any incoming packets too. So let's take away the destination port 53 part, and success, our rule is now alerting on all malware related packets. But it looks like Alabaster needs some more help. He has a Word document which was sent just before the ransomware outbreak. This could be the initial infection vector, so he wants us to analyze it and hopefully identify the domain it communicates with. We're given the document as a zip file and can extract the docx inside with the password elves given to us by Alabaster. We can use OLE-VBA to analyze and extract macro virus code without having to open the document in Word, and hence risk detonating the malware and infecting our own machine. But naturally, we're using an expendable virtual machine for any malware analysis, just in case something goes awry. Here we see two identical functions, one run on the document open event, and one as the auto open function. We can effectively consider them functionally equivalent. The code launches PowerShell and seems to execute a payload which is base64 encoded. Let's head on over to CyberChef once again to decode it, which spits out a bunch of binary data. If we examine the macro again, we can see there's also a decompress function. One of the great things about CyberChef is being able to add and combine multiple functions. So let's add on a decompress function. There's a few to choose from, so let's pick each in turn and see what the result is. After a little trial and error, we see some code. It's a bit messy, but again, CyberChef has a function to make it pretty. It's not perfect, but it's better than nothing. And this code verifies our previous suspicion. It calls out to a domain, then takes the result as a number, and loops through further subdomains to pull down more code and eventually execute it. We can submit our malicious communications domain to Alabaster. He wants us to keep analysing though, this time specifically looking for similarities to another recent ransomware strain which had a kill switch built into it. The obvious reference here is WannaCry, which would stop its infection routine if a particular domain were registered. Alabaster suspects the same may be true of this malware. To get started, we need a copy of the full malware downloaded by the dropper. We can take the dropper code decoded by CyberChef, clean it up a little, and defang it by, instead of executing what is downloaded, just store it in a variable and print it out. The code returned is minimized, so we'll need to make it a little more human readable. I chose to do this in Notepad++, as it has some very powerful search and replace capabilities as well as syntax highlighting. After some initial tidying and taking a brief browse through the main code blocks, we can identify a function at the top of the file which performs cryptographic functions of some sort, a series of functions which are converting data from various formats to another, some code for compression and decompression, a SHA-1 hashing function, more crypto code, some functions making DNS calls, similar to what we saw in the dropper, and finally the WANC function, which seems to be doing a range of different things. Finally, at the end of the file, we see the only code outside of a function block, and therefore the code which is initially executed, is a call to that WANC function. This function must be the main program control loop for the malware. Now that we know that, Let's go ahead and delete that line altogether, which will help us avoid inadvertently detonating the malware on our own machine. Next, let's make WANC a little easier to read by fixing the indentation. Now we can start to examine the function line by line, adding in comments with what we know. The first line just puts some data into the S1 variable. The next two lines are if statements, which, if true, call return to exit the function. As this is our main program loop, they'll stop the program from executing. The first statement is based on some DNS resolutions, so is quite possibly our kill switch. The second checks for the presence of a particular socket on the local host and checks if the machine is joined to the Kringle Castle domain. So this suggests the malware is specifically targeted at Santa's castle. Examining the first if statement in more detail, along with the referenced functions at the top of the malware, we can calculate that it takes the data from the S1 variable, converts it from a hexadecimal string into binary, runs that through a gzip decompression algorithm, converts the result back into a hexadecimal string, exclusive ORs that with a value which is obtained from a DNS request, converts that from a hex string into binary, and then finally into an ASCII string. Performing all these steps manually to identify the kill switch domain would be really laborious, but we can just run certain lines of code in PowerShell and get it to do the hard work for us. Here I've copy and pasted all the code into PowerShell IDE, as we'll need to call on many of the functions defined near the top of the code. Then at the bottom, I've duplicated the couple of lines which look like they calculate the kill switch domain and modified them a little to just print out the domain rather than checking whether it has been registered or not. This kill switch domain is very similar to the password from objective number 4. Clearly the maps we found in the zip file belong to the same person who made this malware. We can go ahead and register this domain using the North Pole domain registry, ho 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 daddy, and we have successfully stopped the spread of the malware. But our work here is not yet complete. Alabaster made the mistake of analysing the malware on his host computer, and the ransomware encrypted his password database. He's provided us with a memory dump from the malware process and a copy of his encrypted database, and would like us to try and recover the crypto keys and decrypt his database. A good place to start is understanding how the malware creates and stores its crypto keys. The function ed file could be short for encrypt and decrypt file, as it takes a key as an input and looks like it does lots of crypto stuff, including calls to a create encryptor and create decryptor function. Let's see what calls it. There's only one reference to it, and that's from a function end. Let's tidy these two up to make them easier to read. Our guesswork seems to be correct. ed file will encrypt files if encrypt is true, and decrypt them if false. And the end function doesn't do any key management itself, but rather takes a key as an argument. Looking for where end is called, we see two references. Firstly, in the top section of our main program loop, where the third parameter is true, indicating that this is the encryption call, and second, near the bottom of our main program loop, where the third parameter is false, meaning this is the decryption call. We know our encryption call is using the value in b_k as the crypto key, so we can break down each of the lines leading up to the encryption call to figure out how that key is being generated. Here we see the code creates an array of all characters 0 through to 255, plus all characters again, plus digits 0 to 9, then randomizes the order of that list, and then takes the first 16 bytes as the key. It then creates a hexadecimal representation of the key and the SHA-1 hash of that. Given that the key is generated using a reliable source of randomness, we'll not be able to compute what the key is, so we'll have to go looking for traces in memory. Thankfully, Alabaster provided us with a memory dump. After extracting the files from the zip, we can use the power dump tool to analyze the memory of a PowerShell process. It takes a few minutes for the tool to analyze and extract information from the memory dump. Finding b_k will be tricky, as it's just 16 bytes containing many possible values, so let's try searching for the hex representation instead, as we know this must only contain digits 0 to 9 and letters A to F. We can do this with a regular expression, and then narrow down our search to variables of only 32 characters in length. We have 5 possible results, but remember we also know the SHA-1 hash of the key was calculated, so we can also search for that to verify which of the 5 possible values is the correct one. SHA-1 hashes are 20 bytes long, or 40 bytes when stored as a hexadecimal string, and we get a single hit for a hex string of this length. With a little bit of PowerShell, we can calculate the SHA-1 hash of each and deduce that none of the 5 candidates seem to match our SHA-1 hash. Maybe that isn't a hash after all. We can just try decrypting Alabaster's database with each of the 5 keys, as 5 isn't too many to try one by one. But once that's complete, we see that none of these files are of any known file type, and they contain what looks like junk. Maybe none of those 5 keys were the crypto key after all. If we examine the code a bit closer, we see that is indeed the case. Straight after calling the encryption routine, the malware erases both the binary and the hex representations of the crypto key. But if we follow the life of b_k a little more, we see it's also used as a parameter in a call to the pke function, which looks to be encrypting our victim's cryptographic key with a public key. Here I've continued to tidy up and annotate the code to piece together a more detailed picture of the malware's operation. After testing for the kill switch and verifying the code is running on the intended target's machine, a public key is downloaded via the same DNS method that was used by the dropper. A separate crypto key is then generated, which will later be used to encrypt the victim's files. A hexadecimal version of this key is created, and a SHA-1 hash of that calculated. The victim's key is then encrypted with the attacker's public key, which is then sent over DNS to the attacker. The DNS call returns an ID number to uniquely identify this victim. The current date and time gets recorded in a variable, followed by the creation of an array which contains all the files which should be encrypted. Only then are the files actually encrypted. And as mentioned before, the victim's crypto keys are finally wiped from memory once that encryption process is complete. A similar analysis of the code around the decryption routine indicates that regular calls are made to a certain DNS address specific to this victim ID. If a 32-byte value is returned, then this should be treated as the decryption key and shown to the victim. Otherwise, the victim continues to receive a ransom unpaid message. This DNS call will presumably only give away the key once the ransom has actually been paid, so that leaves the only trace of our victim's key being in the variable pkek, which is encrypted with the attacker's public key. Is there any way we can get our hands on the private key and extract the victim's crypto key from pkek? After much searching and many dead ends, I took a closer look at the function used to download the attacker's public key, and it's almost the same as a call used elsewhere to download some HTML which gets displayed to the victim. And it's the difference between these two calls which provide the final piece of the puzzle. One call specifies the DNS to source the content from as a hexadecimal string, whereas the other is a file name which gets converted to a hex string. Presumably that string of hex in the first call is a file name. Yes indeed, it's server.crt. Has our attacker been foolish enough to leave the corresponding private key accessible via the same route? They have indeed, and we have our private key. So now we need to extract the pkek variable content from memory. But what does it look like? How can we find it? We see from the code that it's returned as a hexadecimal string, but how long is it? We can run our own version of the key generation code to find out that it should be 512 bytes long. And a search of our memory dump throws up one item of this length. I spent quite a lot of time trying to create a decryption function in PowerShell, but failed miserably. It didn't take too long, however, to find the little Python code snippet which could be tweaked to work in this scenario. Here I have both the private key and the encrypted key stored on disk, the latter converted to base 64 as this is what this particular Python script expects. And here's a quick glimpse of the script itself. The output file produced is 16 bytes long, which is our victim's crypto key in pure binary. We can use the xxd command to get the hexadecimal representation, which, once fed into our previous script, shows that the SHA-1 sum matches what we are looking for. We can go ahead and run the decryption code with this key, and the Linux file command identifies the resulting file as a SQLite database. From here, it's trivial to open the database, examine the schema, and dump the contents to identify the vault password entry. I'll see you in the next episode for our 10th and final objective, where we'll find out who was the mastermind pulling the strings behind Hans and his toy soldiers.